This is the last chapter relating to the reactions of carbonyl compounds. Specifically in this chapter, we're going to cover the carbonyl condensation reactions. Carbonyl condensation reactions involve two carbonyl partners. In general, one of the carbonyl compounds will be converted into an enolate, and then that enolate will act as a nucleophile to add to an electrophilic carbon on another carbonyl partner. This is the general mechanism of some of the carbonyl reactions we're going to cover in this chapter. The reaction starts with a carbonyl compound. A base is added to it, which removes an alpha hydrogen to form an enolate, as shown here. You might recall enolates have two resonance forms. This is one of them. In the next step of the carbonyl condensation reaction, the enolate will nucleophilically add to another carbonyl partner to the carbon of the carbonyl specifically, as shown, to give us this intermediate, which then is protonated to form a beta hydroxy carbonyl compound. Note that in this reaction, we will be forming a carbon-to-carbon single bond. Condensation reactions are those organic reactions that involve joining two molecules to make a larger, more complex structure, and usually a small molecule such as water is produced as a byproduct. The aldo reaction is an example of condensation reaction. The aldo reaction in the classic sense is a reaction that produces a product that contains both an aldehyde and an alcohol. Now we're going to see some examples also that involve a ketone and an alcohol in the product. Below is an example of an aldo reaction involving acetaldehyde. If we add sodium hydroxide, which is a base, the base will deprotonate the alpha hydrogen, creating an enolate, which you see here in this intermediate. The enolate will then attack another aldehyde, specifically another molecule of acetaldehyde, to do a self-condensation reaction. In other words, two acetaldehyde reactions are joining together. The product that we form is a beta hydroxy carbonyl compound or a beta hydroxy aldehyde. In other words, an aldo product. We see an alcohol at the beta position of this aldehyde, and notice also there is a new bond created between the alpha carbon of one acetaldehyde molecule and what turns out now to be the beta carbon of this product, but originally it was the carbonyl carbon of another acetaldehyde molecule. A byproduct of this reaction is a hydroxide ion, and therefore we're essentially regenerating the base that we started with. So sodium hydroxide in this reaction is a catalyst. Aldo reactions in general are reversible reactions, and in many cases, especially with most ketones and many aldehydes, especially those that are sterically hindered, the reaction is actually favored towards the carbonyl compound rather than the aldo product. We can see here a couple examples, and if you notice in the second example, we have a cyclohexanone reacting with each other under the influence of a base, producing an aldo product. Notice that the starting ketone is actually favored in this reaction. Now, to avoid this issue of producing a product that is less stable or less favored than the reactant, for a reversible reaction, specifically the aldo reaction, one of the things that we do to push the reaction towards products is eliminate this hydroxyl group at the beta carbon by adding a base, which removes this hydrogen, the alpha hydrogen of the carbonyl, to do an elimination, which also leads to the elimination of the hydroxyl group. Overall, we are eliminating essentially a water molecule, and removing that water molecule from the aldo product actually pushes the reaction towards the product. And so that's one way to make the aldo reaction a practical reaction in the lab. As a side note, the retroaldo reaction refers to the reverse of the aldo reaction. So if we started with a beta hydroxycarbonyl, like you see here on this slide, and it goes back to the original ketone, we refer to that as a retroaldo reaction. Now, at a dehydration reaction of a beta hydroxycarbonyl product, which is the typical aldo product. If we have a beta hydroxycarbonyl, such as this, and we add either acid or base, we can perform an elimination reaction of water and produce a conjugated carbonyl compound. Specifically, we will have a double bond being formed between the alpha carbon and the beta carbon of the carbonyl compound. If we add base to a beta hydroxycarbonyl, aka an aldo product, the base will remove the alpha hydrogen from, notice this is the alpha position of the carbonyl. Once it removes the alpha hydrogen, we form a double bond here, break the carbonyl to form an enolate, and then the enolate will push out the OH molecule. So the negative charge on this oxygen will reform a carbonyl, then the double bond of the enolate will form a double bond here between the alpha and beta carbon after it eliminates the OH group. Notice that this reaction shown here is a reaction we have seen before, previously in this semester. It is an E1CB reaction. We can also remove a water molecule from a beta hydroxycarbonyl by adding acid. In that case, the alcohol will be protonated first, and then the enol of this carbonyl, remember enols are always in equilibrium with carbonyl compounds, the enol will eliminate that protonated alcohol as follows. So a base, although it's not shown here, a base will remove this proton on the enol, then it will lead to forming a carbonyl. The double bond will move this way between the alpha and beta carbon, and the water molecule, which is a great leaving group, is eliminated, producing an alpha beta unsaturated carbonyl, otherwise known as a conjugated enone or conjugated carbonyl compound. You may have noticed that the conditions for eliminating a water molecule from a beta hydroxycarbonyl is essentially the same conditions that we use to form the aldo product in the first place. As a result, many times it is often difficult to isolate the typical aldo product, which is the beta hydroxycarbonyl. Many times that product actually eliminates from the or it loses water to form an alpha beta unsaturated carbonyl. This is certainly true if we heat the reaction under basic conditions, as we see with this example. If we have cyclohexanone and we add sodium hydroxide, the hydroxide will remove a proton from the alpha carbon, forming an enolate, and then that enolate will react with a second molecule of cyclohexanone to produce the following aldo product. So notice on the top side we have a cyclohexanone, that's the one that forms the enolate here, and then that enolate attacks the carbonyl carbon of a second cyclohexanone molecule, which now is actually shown as an alcohol since it was attacked by the enolate. Under the same conditions, which is base, especially if we heat it, we can now do an elimination reaction, in other words, an E1CB reaction, where base removes the alpha hydrogen here, leads to forming a double bond by eliminating the leaving group, which in this case is a hydroxyl group. So we produce an alpha beta unsaturated carbonyl, which is our condensation product. And then we also obtain a small molecule of water. Let's look at 3 more examples of the aldol reaction involving a dehydration reaction after the aldol reaction. So if we have an aldehyde, such as this one, and we add base and we heat it, we're generally going to have a dehydrated product at the end of the aldol reaction. So the way you can predict the product that you draw, you want to have an aldehyde that you originally started with. So that would be this one going in this direction. And that carbon, which is the alpha carbon, is going to form an enolate. That enolate attacks a second molecule of the aldehyde, of the same aldehyde, and forms a bond. So imagine first forming a single bond here. And then we have the same number of carbons that we have in the aldehyde, which are 1, 2, 3, 4, and 5, which is what we have in the aldehyde, 1, 2, 3, 4, and 5. Now, originally, we're going to have an alcohol in this direction, but after dehydration, we eliminate that alcohol, we remove a hydrogen from the alpha position, so we form the double bond here. Another way of thinking about this is, or predicting the product that we're going to draw, we want to draw the same carbonyl compound, in this case the aldehyde, which we do here, then form a double bond from the alpha position to what typically is the carbonyl carbon, so that would be this carbon, and then add whatever alkyl groups we have on the aldehyde, which are 4 more carbons in this case. Here's an example with a ketone. So again, sodium hydroxide, heat, and usually we use a protic solvent, an alcohol, water to dissolve the sodium hydroxide. The product, again, we can draw that by drawing the original ketone, which we see here on the top highlighted as I'm going through it. And then from the alpha carbon, either one, so it could be the right side or the left side. In this case, it doesn't matter because it's a symmetrical ketone. We want to draw a double bond, which is essentially taking the place of the carbonyl of a second ketone. And then from there, we draw the same carbons or carbon chains that we have on the ketone, which are a propyl group in one direction and a propyl group in the other direction. So we're going to draw 2 propyl groups, one to the right and one to the left from the other end of the double bond. Here's another example with sodium hydroxide, water, and heat. We're going to react with this ketone. Again, to draw the product, we want to draw the ketone, which you can see one molecule of that same ketone right here. From the alpha position, which is this one, we're going to draw. So here is the alpha position of that ketone. We're going to draw a double bond from there, which is going to take the place of this carbonyl on a second molecule of the same ketone. Then we're going to draw a methyl and a phenyl group, just like we have in the starting reactant. Let's practice what we learned about aldol reactions. We're going to start by simply drawing an enolate first of this aldehyde. So we have here an aldehyde with 4 carbons. So in order to draw an enolate of an aldehyde, we want to take a look at the alpha carbon, and we want to remove one of the alpha hydrogens on that carbon, as shown here, to form an enolate. Now, a second possible way of showing this is drawing the resonance form of this structure. So I'm going to use a skeletal structure. The original ketone had 4 carbons. So there's the 4 carbons poorly drawn. And instead of having a negative charge at the alpha carbon, which would be this one, we can actually have a double bond that way, a single bond to the oxygen. Here's our oxygen, and then we could put a negative charge on that oxygen. Question, we want to draw the enone that is obtained from the aldol condensation reaction of acetaldehyde. So what this is really asking us is draw the aldol product and then after that, draw the dehydrated product from the aldo reaction of acetaldehyde. The structure of acetaldehyde, which is an aldehyde that has two carbons or it has a methyl group on an aldehyde. Now, if we add base to acetaldehyde, one molecule of acetaldehyde, let's say the one on the right here, will react with base, form an enolate, and then that enolate attacks the carbonyl of a second aldehyde to form what we see here, which is the typical aldyl product, which is the beta hydroxycarbonyl. So we see a hydroxycarbonyl at the beta position of this aldehyde. Another way of thinking about this is if we look at the right side of this product, here is our original acetaldehyde, and we're going to draw a bond from the alpha position, which is where the enolate forms, to the carbon of a second aldehyde molecule, in this case acetaldehyde. And the carbonyl becomes an OH group as we see by this bond rather than the typical carbonyl that was originally there. So we're joining two acetaldehyde molecules. One is the enolate, the other one is the electrophile. The electrophile typically forms the alcohol. Now that product, at least if we heat it under basic conditions, usually loses a water molecule by losing that OH group as well as this alpha hydrogen. And so we end up with instead a double bond where the OH and hydrogen were. So this is what we sometimes refer to as an enone or an alpha beta unsaturated carbonyl. You could also go directly from the aldehydes to the product by drawing, I'm going to use a different color, by drawing the aldehyde, which is shown here. This is acetaldehyde, and drawing a double bond from the alpha position, which is where the enolate forms, to the carbon of what is the carbonyl carbon in one of these aldehydes. So instead of having a carbonyl, we have a double bond there joining the two acetaldehyde molecules. And then we just draw a methyl group and a hydrogen, just like we have in acetaldehyde, which is a hydrogen and a methyl group. In this question, we're going to try to predict the ketone or aldehyde reactant that is used to make the following aldo product. Notice this is the dehydrated product. In this reaction, we want to predict the aldehyde or ketone that would be used to make the following enone or alpha beta unsaturated carbonyl. So looking at the aldo reaction backwards, we want to look at the two possible aldehydes or ketones involved. So if we notice, we have here a carbonyl compound that has an ethyl group to the right, and then we have this alpha carbon, and then we have a methyl group from there. So one of the two reactants would be the structure that I highlighted there. If you notice, that is 3-pentanone. So we have a carbonyl on a 5-carbon chain. And then the rest of the molecule gives us a hint about the other reactant. So we have here a compound that joins the alpha carbon of the carbonyl that I already highlighted. And we also have an ethyl group to the left and to the right of it. So taking this structure, which I highlighted on the left, we get the other carbonyl compound. So if we replace the double bond with a carbonyl, that would give us the other carbonyl reactant, which is also 3-pentanone. So this is an example of taking two molecules of 3-pentanone to make the product that we started with here. Up until this point, we have looked at what are called self-condensation aldo reactions. In other words, we take one aldehyde or one ketone molecule and we react it with itself to make the aldo product. Now, it is also possible to do what we call a mix or a cross-aldo reaction. This involves taking two different aldehyde molecules or two different ketones or an aldehyde and a ketone to make an aldo product. When we do a mix or a cross-aldo reaction, it is possible that we can obtain up to 4 aldo products. And therefore, the reaction is not practical unless we can narrow down the number of products we can obtain from the reaction. Over the next few slides, we'll cover some strategies that are used to obtain a single product in a mix or a cross-aldo reaction. One of the methods that we can use to obtain a single aldo product from the cross-aldo reaction is to use one carbonyl partner that does not have alpha hydrogens and therefore can't form the enolate. That immediately reduces the number of possible products from 4 to 2. In addition, by using an aldehyde and a ketone, generally, since aldehydes are more electrophilic than ketones, we can ensure that the aldehyde will be the electrophile in the reaction. And combining an aldehyde that can form an enolate with a typical ketone, we can ensure that a single aldo product is obtained from the cross-aldo reaction. Here's an example using 2-methylcyclohexanone and benzaldehyde. If we add base, the base will remove one of the alpha hydrogens on the ketone. Notice the aldehyde, benzaldehyde, can't form an enolate since there are no alpha hydrogens on this aldehyde. The only alpha hydrogens would be on this carbon, and that carbon does not contain any alpha hydrogens. And then also notice that benzaldehyde is more electrophilic than a ketone. So once you form an enolate from this ketone, it would always attack the aldehyde. That would be the electrophile. And as a result, this is the only possible aldo product from this cross-aldo reaction. Notice that initially you will have an OH here where the aldehyde used to be. But after dehydration, that alcohol is removed, as well as a hydrogen that was here in the alpha position, the second alpha hydrogen. So by eliminating this hydrogen and eliminating the OH group, we get a double bond there, and that will be our final alpha beta unsaturated aldo product. One term that you should be familiar with as far as condensation reactions is that we often refer to one of the partners as the donor. The donor refers to the ketone or sometimes aldehyde that can form the enolate. And so therefore it is the nucleophile. The way to remember it, it is the partner that is donating electron density, in other words, the nucleophile. And then another term that we use with condensation reactions, including the aldo reaction, is the acceptor. That refers to the electrophile in the reaction, the one that accepts electrons. So in the example above, benzaldehyde is the acceptor. The donor is this ketone on the left, which is the one that forms the enolate. Another strategy that we can use to get a single product from the cross-aldo reaction is a partner that has a very acidic alpha hydrogen. So a good example would be a 1,3-dicarbonyl. So in the example shown here, we have a 1,3 keto ester as one of the partners. That will ensure that this is the partner that forms the enolate. So base will remove the highlighted hydrogens in blue, one of them. That forms the enolate, and then so that will make this compound the donor. That enolate then attacks the ketone on the left, which is the acceptor, to form the following aldo product. So again, notice the product has the 1,3-diester or ketoester here, and we're forming a double bond between the alpha carbon to the carbon that is part of the ketone on this side. So this is the rest of the ketone, and we're essentially swapping the carbonyl of that ketone with a double bond to the alpha hydrogens or the alpha carbon on the aldo donor. First strategy that we sometimes use for the cross-aldo reaction is to use LDA as a base, which completely should convert any ketones into an enolate. And so we're pre-forming the enolate, and then we add that enolate in a second step to a flask containing another aldehyde or ketone, which will react as the electrophile. So here's an example of how that would work. LDA at negative 78 degrees is added to this ketone. Since we're using LDA, we generally will obtain the kinetic enolate. So that would be forming an enolate from this carbon. And then that carbon will add to the carbonyl of the aldehyde that we add in the second step. It'll break the double bond of the carbonyl. That oxygen then gets protonated in the third step of the reaction to become an alcohol. So initially we form this beta hydroxycarbonyl. Beta hydroxycarbonyls in general are fairly unstable, so heating them with either acid or base generally leads to the elimination of water and forming a double bond. And so that's what we see here. If we add sodium hydroxide or sulfuric acid and we heat the reaction, we can obtain a dehydrated product by removing this alpha hydrogen, which should, so if we use base at least, we will remove this hydrogen, form a double bond here by eliminating this alcohol. In the case of sulfuric acid, as we saw earlier, generally sulfuric acid will protonate the alcohol, and then the enol of this ketone will push it out to form the double bond. In this question, we want to show the likely reactants that we would use to make the following alpha beta unsaturated ketone through a aldo reaction. In order to predict what carbonyl compounds could be used to make this alpha beta unsaturated product, which we typically obtain from an aldo reaction, we want to focus in on this carbonyl here all the way up to this double bond. So if we replace or we add two more hydrogens making this a methyl group, we would have the original ketone, which we see here. So this is our aldo donor. On the left side, we have the aldo electrophile, the aldo acceptor. It has a phenyl ring, so C6H5, as mentioned here, is a benzene ring, and that's attached to another carbon, which would have a carbonyl, at least to begin with. So that gives us benzaldehyde. So essentially, we swap this double bond here in the middle with a carbonyl, and that's how you get the other partner. Some dicarbonyl compounds are set up perfectly for an intramolecular aldo reaction. Generally, if we can form a 5 or a 6-member ring in an aldo reaction, an intramolecular aldo reaction, then such a reaction is most likely to occur. As an example, 2,5-hexadienone, which is a 1,4-diketone, when treated with base, can form or can lead to an intramolecular aldo reaction. So base will remove one of these alpha hydrogens, forming an enolate at that carbon. which would then attack this carbonyl. And then after elimination of the hydroxyl group, we would achieve a double bond as well as closing the 5-member ring. In the next example, we have a 1,5-diketone. And again, when treated with base, it would form an enolate at that carbon, which would cyclize here on this carbonyl carbon. After elimination of the hydroxyl group, we would have a double bond between the alpha carbon here and the carbonyl there, or the carbonyl carbon there. And so we would have now a 6-member ring that has a double bond. Let's take a closer look at 2-hexane dione and how it forms a cyclic enone. If we add base to this dicarbonyl compound, there's 2 possible alpha hydrogens that can be deprotonated. So if we remove this one, as we saw on the previous slide, we can cyclize onto this carbonyl to form this beta hydroxy carbonyl initially, and then base would remove another alpha hydrogen, form a double bond here by eliminating the hydroxyl group. And so we end up with a cyclic enone as a product. The alternative reaction, which we didn't observe in the previous slide, would occur by removing instead an alpha hydrogen from the other carbonyl. So here's this carbonyl. If we remove an alpha hydrogen here, that alpha hydrogen will, or removal of that alpha hydrogen will lead to an enolate on that carbon, which could cyclize onto the other carbonyl to form a 3-member ring with a hydroxyl group that is beta to this carbonyl, and removal of the other alpha hydrogen with base and elimination of the hydroxyl group leads to a double bond. Of course, this is not a product we typically observe given the strain in this 3-member ring. This is a much more favored pathway, and this is what typically is observed, not only in the aldol reaction, but any cyclization reaction. In general, any reaction that leads to a cyclic 5-member ring or 6-member ring, generally that's a favored pathway compared to any other type of ring. Collagen is the most abundant protein in mammals. It makes up around 25% of all the proteins present. As animals age, collagen becomes cross-linked through imine shift bases or through aldol condensation reactions. Here we can see a simplified version of these types of reactions. Collagen molecule has an NH2 group from a lysine amino acid, and that amino group can react with the aldehyde of glutaraldehyde, forming an imine, which I've covered previously in this semester. Some of the aldehyde residues from glutaraldehyde can react through an aldol condensation reaction, producing a polymer. We can see here a portion of the product that results from the aldol reaction. So we have an aldehyde, and at the alpha position, we have a double bond that would result from the alpha carbon of this aldehyde reacting with a different aldehyde unit through an aldol reaction. In addition, we can get another formation of an imine base, as shown with this product. In this question, we will try to determine the product from an intramolecular reaction of this diketone with base. When we react this symmetrical diketone with base, we're going to form an enolate that, although initially looks like we have 4 possible places we could form the enolate, in reality, because of the symmetry of the molecule, there really is only one enolate that we form. So as shown with this structure here, we have an enolate at the alpha carbon of one of the carbonyls. And if that enolate reacts with the carbonyl, the other carbonyl, we close the ring to form this alkoxide intermediate, which if we stretch out the rings looks more like this, and you can clearly now see that there is a 5-member ring on this side and a 7-member ring on that side, on the right side with a ketone. If we protonate the alkoxide intermediate with an alcohol, we will get now a beta hydroxycarbonyl. So this is the typical product of an aldo, at least initially. So this is the alpha position, the beta position, and if we heat this intermediate with base, we can remove an alpha hydrogen to eliminate this alcohol and get a double bond in the process. So this should be our dehydrated aldo product, the one that we should expect from this reaction. Now, because of the symmetry of this molecule, we don't need to focus on forming an enolate from this other ketone. It's going to be the same enolates as the one on the top. And actually, forming an enolate on this side of the carbonyl is the same thing as forming an enolate on this side. And you can confirm that by trying to draw the product that would form from the enolate of this carbon attacking this carbonyl. It should lead to closing a 5-member ring in this direction. So if we count the carbons, 1, 2, 3, 4. So let's finish that 3, and then 5. And in this direction, so going towards the left of the carbonyl, so starting from this carbon, going in this direction, we're actually going to have 7 carbons. So we'll actually end up with the same product. So initially, you will see the 7-member ring on the left side and the 5-member ring on the right side. But obviously, if you flip that molecule, you'll get the same exact structure as shown here. Another classic condensation reaction between carbonyls is called the Claisen condensation. This is when 2 esters react with each other. We'll start with an example of a self-condensation example involving ethyl acetate. If we add base, such as sodium methoxide, one molecule will form an enolate, so let's say it's this one, that would attack the other ester, eliminating the ethoxy group and forming this beta ketoester. This is the typical Claisen product. You might recall that aldo reactions typically will give you initially a beta hydroxycarbonyl, and then that dehydrates to form an alpha beta unsaturated carbonyl. In the case of the Claisen reaction, we typically get a beta ketoester. We also usually get a small molecule like ethanol or some other alcohol that is the leaving group on the ester. Notice that the base that we typically use is usually the conjugate base of the leaving group that we're going to be using for the ester. So we have ethoxy groups on the acetate molecule. So that is the base that we will use for this reaction. Let's take a look now at the mechanism for the Claisen reaction. So the reaction starts with a base such as ethoxide deprotonated an alpha hydrogen on one of the ester molecules. That forms an enolate as shown here, which will attack the carbonyl of another ester molecule, forming a tetrahedral intermediate as shown in the next structure. This tetrahedral intermediate will reform the carbonyl by eliminating the ethoxy group, the leaving group on that ester. After eliminating the leaving group, we end up with a beta ketoester, which is the typical product of the Claisen reaction. But in reality, under the basic conditions that we use for forming this Claisen reaction, notice that generally one of the alpha hydrogens on this beta ketoester is usually deprotonated by base, ethoxide for example, to form an enolate, and it is later when we convert this enolate back to the beta ketoester by adding acid. So in the Claisen reaction, we usually include a second step where we have to add acid to get rid of not only the base, but also turn the enolate of the beta ketoester product back to a beta ketoester. In this question, we're going to determine the product from the Claisen condensation of this ester shown here. So we have an ethyl leaving group on the ester, and then besides the carbonyl carbon, we have 2 carbons more, a third one from one of the methyl groups, and of course a methyl substituent. So if we do a self-condensation reaction of this ester shown here in the reaction, and we add base, an alpha hydrogen from the ester will be removed and form an enolate, which then attacks a second molecule of the same ester, eliminating the ethoxy group. That should lead us to a beta ketoester. So the left side of the structure here is from one molecule, that's the electrophile or the Claisen acceptor. And the right side is the molecule that forms the enolate. So that would be this one here. That is our Claisen donor, or the molecule that forms the enolate. Similar to the cross or the mix aldo reaction, the mix or cross Claisen reaction can potentially give you 4 possible products. We can use strategies to eliminate some of these products and hopefully obtain a single product. One of those strategies is to use an ester that doesn't have alpha hydrogens and therefore can form an enolate. And as a result, it will be the acceptor in the reaction or the electrophile in the reaction. Here's an example where that strategy is used. So mixing ethyl acetate and ethyl benzoate plus base should lead to a Claisen reaction where a single product is obtained. So ethyl acetate has alpha hydrogens. So sodium hydride, which is a base, will remove one of those alpha hydrogens, forming an enolate. Then that will attack the ethyl benzoate. The ethyl benzoate, notice, doesn't have any alpha hydrogens, so it's not going to form an enolate. So the enolate of ethyl acetate will attack this electrophile ethyl benzoate and form the following beta ketoester. So in blue is the structure that came, or part of the structure that came from ethyl acetate, and the bond to the carbonyl of what used to be the ester in ethyl benzoate is shown here. We also eliminate the ethoxy group, which becomes an ethanol molecule as a byproduct. Note that using an excess of ethyl benzoate or adding ethyl acetate slowly to the reaction will ensure that the enolate of ethyl acetate, once it's formed, will only see or mostly see other molecules of ethyl benzoate rather than other molecules of ethyl acetate to react with. So in other words, by either adding an excess of ethyl benzoate or adding ethyl acetate slowly, we will ensure that the enolate of ethyl acetate will only react with ethyl benzoate rather than with another molecule of ethyl acetate that hasn't formed an enolate yet. Here's an example of a Claisen-like reaction involving a ketone and a ester. The ketone has alpha hydrogens, so when we add base, one of those alpha hydrogens will be removed to form an enolate. That enolate will then react with ethyl formate. Note that ethyl formate does not have alpha hydrogens, and so it can't form an enolate. So once the enolate of the ketone attacks the ester, it eliminates the leaving group, and you'll end up with this beta keto aldehyde. A second strategy that we can use to ensure that the Claisen reaction goes smoothly is to preform an enolate from one of the esters. That would ensure that one partner is the only one that forms the enolate, and then add in a second ester to act as the electrophile. So in this example, we're using an ester, we're adding LDA to form an enolate on the alpha carbon, and then that enolate will attack the ester we add in the second step, eliminate the leaving group, and form a beta keto ester. You can see highlighted now on the left side of the structure, this is the structure that is added from the ester, this one here, that forms the enolate. And then the ketone and the remaining carbons, so that would be these carbons here, will come from the electrophile of this reaction. In the last example on this slide, we have again an ester, and we're going to add LDA to form an enolate at this alpha carbon. That would react with another ester molecule, forming a beta keto ester. In this question, we want to predict the product that you would expect from a mixed Claisen reaction between the two esters that are shown in this structure, in this example. Comparing the two esters that we have here, notice that diethyl oxalate does not have alpha hydrogens, so it's going to be our Claisen acceptor, while ethyl acetate has alpha hydrogens, which are acidic. So if we add base to it, we'll form an enolate on this alpha carbon. That alpha carbon will then react with one of the two ester functional groups on diethyl oxalate. That will lead us to forming a beta keto ester. So again, the structure or the part of the structure that came from ethyl acetate is shown here now highlighted. And then on the left side, we have what remains from diethyl oxalate once the enolate nucleophile adds to it and displaces the ethoxy group. The intramolecular Claisen reaction is sometimes referred to as the Dieckmann condensation. Just like the intramolecular aldo reaction, we want to form 5 and 6 member rings. With a 1,6 diester, we typically will form a 5-member ring, as shown in the product. Addition of base to this diester leads to forming an enolate in this carbon, which attacks the other ester, forming a cyclic ketone, which has a beta ester, which is external to the ring. In the next example, we have a 1,7 diester, which typically gives you a 6-member ketone with an external ester. In this example, base will deprotonate this carbon, or the hydrogen on that carbon, which then attacks the other carbonyl of the other ester, forming a cyclic ketone with this external ester. Note that this reaction works best when we are working with a symmetrical 1,6 diester or a 1,7 diester. If we have an unsymmetrical diester, then we'll have the possibility of forming 2 or more products. Here's an example of the mechanism for the intramolecular Claisen reaction or the Dieckmann reaction. So base will deprotonate the alpha hydrogens on one of the two esters. That enolate that forms will attack the other carbonyl, breaking the double bond, forming this tetrahedral intermediate. It then reforms the carbonyl by eliminating the leaving group. The resultant product, which is a beta keto ester, just like in the normal Claisen reaction, is very acidic. So under the basic reactions of the Dieckmann condensation, the base will remove an alpha hydrogen, which is in the center of two carbonyls, forming an enolate. And then once we add aqueous acid at the end of the reaction, we can go back to the beta ketoester. Claisen-like condensation reaction occurs in the biosynthesis of cholesterol as well as fatty acids. Generally, the reaction involves transfer of an acetyl group from acetyl coenzyme A onto the thiol group of the enzyme that is involved in this reaction. That leads to this thioester, which will react with the enolate of another thioester of acetyl coenzyme A. So in this step, the alpha hydrogen of this thioester will be removed by base, forming an enolate, which will then attack this other thioester and do a Claisen-like reaction, forming this tetrahedral intermediate, which then reforms the carbonyl by eliminating the leaving group and giving us a beta keto thioester. For example, we have a 1,7-diester that will be treated with base in an intermolecular Claisen or a Dieckmann reaction. The ester that is in this question is a symmetrical 1,7-diester. When treated with base, it will form an enolate out of one of the two esters, and it doesn't matter which one you use since we're dealing with a symmetrical molecule. This carbon will then attack the carbonyl of the ester, eliminate the leaving group, and it should form a 6-member ring. You can sort of map this reaction out by counting or labeling carbons. So that is carbon 1, this is 2, this is 3, this is 4, we have 5 here, and then we have the carbonyl carbon, which is number 6. So in our product, this would be carbon 1, this will be 2, 3 has a methyl group, just like in the reactant, 4, 5, and then the ketone carbon is 6. Remember, that is the carbon that used to be an ester, and we eliminated the leaving group. We also have this external ester, which is this one here. The classic condensation reactions is called the Michael reaction. So this is a reaction where the enolate of one carbonyl compound reacts with the beta carbon of an alpha beta unsaturated carbonyl compound. As an example, if we use a beta ketoester such as this and add base, we'll remove one of these acidic hydrogens in the center of the two carbonyls. That forms an enolate. The enolate will add to the beta carbon of 3-butene-2-one. The double bond electrons will move towards the alpha carbon. That negative charge will then be removed when this compound is protonated by aqueous acid. Notice that the product would be a 1,5-dicarbonyl. So if we count the carbons, we can count the ketone in the product as carbon 1, the alpha carbon is carbon 2, then the beta carbon. And then we start counting now the alpha carbon of the dicarbonyl compound that we use to make the enolate. And you can count towards either carbonyl. So I counted this one as 5, but I could easily do the same with this one. Notice that the product contains both components. So this is the alpha beta unsaturated carbonyl. We just got rid of the double bond between carbon 2 and 3. And we form a new sigma bond between carbon 3 and 4. Carbon 4 is the alpha carbon of the dicarbonyl compound. Two terms that we often use with Michael reactions is Michael donor, which refers to the compound that forms the enolate. So usually we use a fairly acidic dicarbonyl compound or an alkyl nitro compound. Now, if we use LDA, we could preform an enolate from just about any carbonyl, so that's another option. The Michael acceptor would be the electrophile in the reaction. It is typically an alpha beta unsaturated carbonyl or an alpha beta unsaturated nitrile or an alpha beta unsaturated nitro compound. The mechanism for the Michael reaction, it starts off with a base removing a fairly acidic alpha hydrogen that would be found on a 1,3-dicarbonyl compound. That leads to an enolate. The enolate is nucleophilic, so it adds to the beta carbon of an alpha beta unsaturated carbonyl. That leads us to forming this enolate, which then gets protonated to give us the final product, which is typically a 1,5-dicarbonyl compound. There are many possible partners that we could use for a Michael reaction. In general, we want to use a Michael acceptor, that is an alpha beta unsaturated carbonyl or carbonyl-like functional group. Here's a few examples. So we have a alpha beta unsaturated aldehyde. In this next example is an alpha beta unsaturated ketone. We have in the third example an alpha beta unsaturated ester. The fourth example is an alpha beta unsaturated amide. The fifth one here is an alpha beta unsaturated nitrile, and then lastly an alpha beta unsaturated nitro compound. For the Michael donor, the one that forms an enolate, usually we want to have a 1,3-dicarbonyl. So there's a few examples shown here. We have a diketone, a keto ester, a diester, but we can use other compounds that are fairly acidic that can form an enolate or an enolate-like intermediate. So for example, we can have a ketone with a nitrile, one carbon, or actually two carbons away. And then we can use a nitro compound. So nitro compounds tend to be highly acidic. So you only need one single nitro functional group in order to make an enolate-like intermediate. Let's go over a few examples of Michael reactions. So the first one on this slide involves a 1,3-diketone. We're going to react that with base to form an enolate at this carbon. And then that carbon, once it is an enolate, will attack the beta carbon of this alpha beta unsaturated ester. And so we will end up making this bond here. And notice the product would be a 1,5-diester. So if we count from the carbonyl of each partner, they're going to be 1,5 to each other. So this is carbon 4, and you can count the carbon of any of the two ketones. Those are going to be carbon 5. In the next example, we're using a nitro compound, an alkyl nitro compound, which are highly acidic. So this carbon here is the most acidic. It will form an enolate there, and it will attack the beta carbon of this alpha beta unsaturated ketone, and it will end up making this bond here. So notice this is the same structure that we started with here, and it's adding to the beta carbon of the alpha beta unsaturated ketone. So at this position, the double bond will shift over to the alpha carbon, put in a lone pair there, which then gets protonated by acid, and so that's why we don't see anything else in the product at that position. The last example on this slide involves using LDA at -78, which of course would form the kinetic enolate. So that would be forming an enolate at this carbon, the last substituted carbon of the unsymmetrical ketone. It will add to this alpha beta unsaturated nitrile. The electrons from the double bond will go towards the alpha carbon. And so in this reaction, we will make this bond between the alpha carbon of the ketone, the beta carbon of the alpha beta unsaturated nitrile. The negative charge that initially adds at this position will be protonated by acid, so a proton will be added there, and we won't see it in the product since it's a skeletal structure. The Robinson annihilation reaction is a reaction that combines both a microreaction followed by an intramolecular aldo reaction, and it often is used to form rings, and usually or traditionally it has been used to make several steroids in the lab. So here's an example leading to the steroid. Here is called estrone. It starts off with a microreaction involving this ketone, which would be a microdonor. It's a 1,3-diketone to be exact. And it's a fairly acidic hydrogen here in the center. That hydrogen, once removed by base, will lead to an enolate at that carbon. And so that carbon, or the enolate there, will add to the beta carbon of an alpha-beta unsaturated carbonyl. The electrons from the double bond will move and put an enolate at that position. That gives us this intermediate after that enolate is protonated by water or some other acid. If we add base to this intermediate, we can, in effect, do an intramolecular aldo reaction. So that would involve forming an enolate at this carbon, which would then attack the carbonyl here. And after dehydration, we would form a double bond there, which you see here in the product. Now, the reason why that particular alpha carbon is the one that is removed is because it leads to closing the 6-member ring, as we see in the product. In this question, we're going to try to predict the product from a base-catalyzed microreaction of 3-butene-2-one with the following microdonor. So this question asks us to predict the product of a microreaction between this diester, which will be our microdonor, and the following microacceptor. By adding base to these two compounds, the most acidic hydrogen, which would be one of these, would be removed, and then an enolate from that carbon would attack the beta carbon of this alpha-beta unsaturated ketone. The electrons in this double bond will move towards the alpha carbon, put in a negative charge there, which after adding acid will turn into or will add another hydrogen on that carbon. So the final product is shown here on the right side of the slide. And the reaction is going to involve making this bond between the CH on the left of that line and the CH2 to the right of it. The CH2 is the beta carbon of the microacceptor. The alpha carbon is the CH2 after it. And then we have the carbonyl with the methyl group. In this question, we're going to look at the microreaction backwards. So we have here a typical product from a microreaction, and you can tell that by the fact that it is a 1,5-dicarbonyl compound. So if we compare this carbon, which is a ester, to the other two carbonyls in the molecule, we'll notice that they're 1,5 to each other. And again, I went towards this ketone, but I could also go in the direction of this other ester on the top, which is also the 5th carbon, away from the first ester where I started counting. So this is a product of a microreaction. You want to think about what two reactants, which microdonor, which microacceptor we want to use to make it. So looking at this reaction backwards, we have the following product here on the right. And we're going to make the bond, which is highlighted here in the reaction. So we're going to take a 1,3-dicarbonyl compound, a beta keto ester to be exact. That's going to be one of the reactants. We're going to break this bond and thinking about the reaction going towards reactants. So Uh, the reactant shown here on the left is our Michael donor, the one that forms the enolate. And we're going to react it with this Michael acceptor. And so remember, the Michael acceptor is always an alpha beta unsaturated carbonyl of some sort. In this case, it would be an ester. So if we add a double bond between these two carbons, we'll have now a double bond between the alpha and the beta carbon of this ester. So here is our other reactant. In our next condensation reaction, we're going to be using enamines as an equivalent to enolates. So before we get into the next set of reactions, let's review how enamines are formed. So you might recall that enamines are typically made by taking a secondary amine, and in this case we're using a cyclic one, but it doesn't have to be. So as long as it's a secondary amine, and we're going to mix that with a ketone or an aldehyde to form an enamine. So an enamine you can recognize by the fact that there's a double bond, and on one of those carbons you have a bond to an amine. So this reaction is reversible, and if you might recall, if we add water and acid to the enamine, we can go back to the ketone and amine that we used to make it. The amines are always going to be secondary amines whenever we make an enamine. Are very similar in their reactivity to enolates and enols. So we can draw an enol here as well, which actually looks a little bit more like an enamine. But in whichever one of these we look at, we notice that the alpha carbon is always nucleophilic. So here's the enolate of a typical ketone, which has two resonance structures. So again, a ketone, if you add base, you can form an enolate. And then the enolate, we can draw two resonance forms of it. So one has a negative charge on the oxygen, like shown with this structure on the left. The other resonance structure has a negative charge on the carbon. For enamines, if we push electrons from the nitrogen towards the alpha carbon, we will have a resonance form that has a negative charge on that alpha carbon. So just like enolates, the alpha carbon is nucleophilic. Enols, as we've seen in the past as well, they're nucleophilic at the alpha carbon. So we could draw another resonance structure similar to what we did with enamines, which has a negative charge on this alpha carbon. We have now a double bond here, an oxygen with a hydrogen. So this is the reason why enols, enolates, and enamines are sort of lumped together. They all have a structure that is typically made from a carbonyl compound, and it makes that compound nucleophilic at the alpha carbon. Due to the similarities in reactivity between enamines and enolates and enols, enamines can do similar reactions as both enolates and enols. In other words, for example, we can do alkylation reactions at the alpha carbon. So if you have an enamine as shown on this slide here on the top, if we add an alkylating agent, we can add an ethyl group to the alpha carbon, which would be this one here. If we follow the reaction with aqueous acid, we can convert the intermediate of this enamine into a carbonyl compound. The reason for that is, remember, the formation of enamines is a reversible reaction. So if we add aqueous acid, we could go back to the original, or go back to a ketone or an aldehyde plus a secondary amine, which is what we did here. So in this example, we made a bond between the alpha carbon, which is this one here. So this is the alpha carbon of the enamine. And we made a bond to the ethyl group of the alkylating agent. So that carbon there would be this carbon here. And then the enamine, nitrogen, gets hydrolyzed into this ketone, and then we also have an amine byproduct. This next example will probably make it a little bit clearer of exactly what's going on here. So if you have an enamine and you add an alkylating agent like this alkyl halide, the enamine will push electrons towards the alpha carbon, which will then attack the carbon with the leaving group. That forms this intermediate. So we have just formed this bond here between the alpha carbon, this one, and the carbon that had the leaving group. And what happens to the nitrogen is it forms an iminium ion, which we see here. So as it pushes electrons towards the alpha carbon, it forms that double bond, a positive charge on the nitrogen. And iminium ions will be hydrolyzed by aqueous acid into a ketone and a secondary amine. Enamines will do all sorts of reactions that relate to what enolates and enols do. For example, they can do reactions very similar to the Michael reaction. When it comes to using an enamine, we're essentially replacing the enolate with an enamine in the Michael reaction. And we often refer to an enamine Michael reaction as the Stork reaction. So here's an example. If we start off with cyclohexanone and we add this cyclic secondary amine, we will form the enamine that you see here. So the nitrogen attaches where the carbonyl is, you get an enamine out of it. Then that enamine basically behaves like an enolate, so is nucleophilic at the alpha carbon, which is this one. That alpha carbon will attack the beta carbon of an alpha beta unsaturated carbonyl. That leads to this intermediate. So we just formed this bond here. Notice the nitrogen of the enamine becomes an iminium ion. We form an enolate here at the alpha carbon. When we add aqueous acid in the second step or the last step, it's actually the third step of this reaction. When we add water in this last step, we're gonna do a few things. Number one, we're gonna protonate the carbon. So this carbon here will be protonated and it will become just a regular carbonyl. The iminium ion will be hydrolyzed into a carbonyl and a secondary amine. Here's another example of the Stork reaction, which again is a Michael reaction using an enamine instead of an enolate. So if we start off with an enamine, the nitrogen again will push electrons towards the alpha carbon, which will make that carbon nucleophilic. And that alpha carbon will attack the beta carbon of an alpha beta unsaturated compound, such as a ketone. We now form in this reaction this bond here is reacting the alpha carbon of the enamine with the beta carbon of an alpha beta unsaturated carbonyl. Initially, we're going to have an enolate, and I'm showing here one resonance form, but we could have another resonance form that looks like this, where we have a carbonyl and a negative charge here at the alpha carbon. And you could draw out the rest of the structure if you want, but something like this. So we have the methyl, etc. Okay, that enolate, whether you use this resonance form or this resonance form, is going to get protonated and it's going to become the ketone that you see in the product. The iminium ion here will be hydrolyzed into a ketone, and you're going to get a secondary amine as a product, as a side product. Here's an example of an enamine participating in the aldo reaction as an equivalent to a enolate. If we use this example involving an enamine and we add it to a ketone, this alpha carbon should add to the carbonyl carbon of the ketone. So we would get a reaction between this carbon and this carbon. As a result, this carbonyl, this ketone, becomes an alcohol initially, which you see here in the product. We're forming this bond here between the alpha carbon on the left side of that line and the carbonyl carbon on the right side of that line. Then when we add aqueous acid, the iminium ion that forms from this nitrogen will become a carbonyl, and then we'll get a side product of a secondary amine. The secondary amine should always can be determined based on what you have here in the enamine. So simply that nitrogen will be replaced by water, and it picks up a proton to become the secondary amine. Here's another example involving the mechanism as well to clarify how this reaction occurs. So the nitrogen of the amine will push electrons from the alpha carbon and attack an aldehyde. That initially gives you this intermediate shown here, and then the oxygen picks up a proton from aqueous acid. In addition, this iminium ion becomes hydrolyzed by the aqueous acid to form a ketone. And we get a side product of a secondary amine. Again, notice this secondary amine is related to the nitrogen that we have in the enamine. The nitrogen picks up a proton to become that secondary amine. Many examples of biological aldo reactions involving carbohydrates. Here's an example using this ketone reacting with amino group on an enzyme, an aldolase enzyme, which will form an enamine. So if you see here, we have a carbon-carbon double bond and a nitrogen attached. That enamine can react like other enamines we have seen in this chapter through the alpha carbon, which will be this one, to attack an aldehyde and essentially do an aldo reaction. So in the process, we're going to be forming this bond here. Notice the aldehyde becomes an alcohol, so that refers to this aldehyde. And then the enamine, the alpha carbon of the enamine, will be this one here. Addition of water will hydrolyze the iminium ion. So this iminium ion intermediate will be hydrolyzed into a ketone, which we see here in fructose. Here's another example of an aldo reaction from a biological system, this time involving type 2 aldolases, which are typically found in fungi and bacteria. It starts off with this ketone, which is converted into an enol. So that happens by base removing the alpha hydrogen, and then the carbonyl get protonated, forming an enol. The alpha carbon of this enol is nucleophilic, and so it would add to an aldehyde. The aldehyde oxygen gets protonated to become an alcohol, this alcohol here. In this reaction, we're forming this bond. This is the alpha carbon of the enol that we use in the aldo reaction. And as a result, this is a way to make fructose. In this reaction, we want to use an enamine to prepare the following compound. When you look at this compound, one thing you should notice is that we have a nitrile, and the carbon of the nitrile is 1,5 to the other carbonyl in this product. So this is a sign that we're doing a Michael reaction. We are likely forming this bond in this Michael reaction. And again, you want to use an enamine as the Michael donor. Looking at the product from this reaction, this one here, as we recognize or discussed in a moment ago, this is a 1,5-dicarbonyl compound. So if we consider the nitrile carbonyl, it will be 1,5 to the ketone. And that's perfectly set up for a microreaction that will lead to forming this bond. If we want to use an enamine, enamines are typically made by taking a secondary amine and mixing it with a ketone or an aldehyde. So the ketone to the left of this bond that I just drew, or this line that I just drew, would be used or mixed with a secondary amine to form an enamine. So for example, we would use this ketone and we could use this secondary amine. It doesn't necessarily have to be that one or even a cyclic one, but that's just the example we're going to use. When these two combine, we should get an enamine that looks like this. And then if we add an alpha beta unsaturated nitrile, so that would allow the nitrile to be the Michael acceptor, the alpha carbon of this enamine would add to the beta carbon of the alpha beta unsaturated nitrile, forming this bond here. The alpha carbon of the nitrile would be present now at containing a negative charge. When we add aqueous acid, that carbon gets protonated and it becomes simply a carbon that has two hydrogens in the product. The iminium ion gets hydrolyzed by aqueous acid into a ketone, which we see in the product, and a secondary amine. In this question, we're going to use an enamine reaction to prepare the following compound. If you notice, this product of a enamine reaction has a 1,5-dicarbonyl. So typically, that's a hint that we're going to be using some sort of microreaction. If we're involving enamines, as we discussed earlier, is called a Stork reaction. So this is a Stork reaction, and we want to make the following bond here. So if we draw a line, we're referring to making that bond there. On the left side, we're going to be using, since the question asks us to use an enamine, we're going to use an enamine from this ketone. So if we use that ketone and add a secondary amine, again, it doesn't have to be this particular secondary amine, but any will do. We will make an enamine that we see here. And if we add that to an alpha beta unsaturated ketone, we can make the product that is part of this question. So this alpha carbon will attack the beta carbon. We get rid of this double bond. We're forming this bond between the alpha carbon of the ketone, the beta carbon of the alpha beta unsaturated carbonyl. Notice that beta carbon also has a methyl group, so that's the methyl group sticking up. And then if we continue to count down, beta carbon is attached to the alpha carbon, so this is the beta carbon, this is the alpha carbon. Then we have the ketone and then a methyl group. It's a good idea at this point to summarize the products from the main reactions we cover in this chapter. As we discussed, the aldo reaction typically gives you a beta hydroxycarbonyl, or if you dehydrate it, you'll get an alpha beta unsaturated carbonyl. Another reaction we discussed was the Claisen, or the intramolecular version, which is the Dieckmann reaction. That typically gives you a beta ketoester. The microreaction, or the Stork reaction, which is the enamine version of the microreaction, generally gives you a 1,5-dicarbonyl as a product. Let's now review some of the reactions we covered in this chapter. In the first reaction, we're using a 1,3-dicarbonyl. We're adding base to it and then mixing it with an alpha beta unsaturated ketone. In the next example, we're going to use an enamine, or we could use a ketone plus LDA, which is a base. And then we're going to mix either of those two with an alpha beta unsaturated ketone. In the third reaction, we're using a ketone and an aldehyde plus base, and then we're heating the reaction. In the last reaction on this slide, we're using an ester, adding LDA to it, and then mixing that with another ester. The first example here on this slide is an example of a Michael reaction, and we can tell that from the fact that we're using a 1,3-dicarbonyl and an alpha-beta unsaturated carbonyl. Base would remove one of these protons in between the two carbonyls. That carbon would then attack the beta carbon of this alpha-beta unsaturated carbonyl, leading to the formation of this bond here. The product should have, like all Michael reactions, a 1,5-dicarbonyl. So if we count the carbons from one ketone, from the Michael acceptor, to one of the other carbonyls from the Michael donor, there should be 1,5 to each other. In the next example, we're going to use either this enamine or this ketone with base to attack an alpha-beta unsaturated carbonyl and do a Michael reaction. So the enamine is nucleophilic at the alpha carbon. A ketone, if we add base, would remove a proton from this carbon, which would make that carbon nucleophilic. In either case, that carbon, either from the ketone or from the enamine, will attack this beta carbon, leading to the formation of this bond. This is the beta carbon of the Michael acceptor. This is the alpha carbon. The next example is an example of an aldo reaction. So if we use a ketone and we add base, we should remove one of these protons. Because the ketone is symmetrical, it doesn't matter. Then that ketone, that enolate from the ketone, would add to this aldehyde. Notice this aldehyde does not have alpha hydrogens, so it can't form an enolate. So the ketone enolate will attack the aldehyde, and after dehydration should form a double bond there. So we're forming this bond here initially, turning this aldehyde into an alcohol. So you'll have an OH here initially, but then we lose that OH plus a hydrogen here, and that's the reason why we have a double bond instead in the product. In the last example, we have an ester. If we add LDA, it should remove an alpha proton from here. That carbon will now attack the ester. So this carbon would attack the ester, eliminate the methoxy group to give you a ketone that is beta to the ester that we use as an enolate. So this is the ester that we're starting with. So that would be this ester. It's just drawn a little bit different. We want to make a bond between the alpha carbon to the carbonyl of this ester. In the next question, we want to use an enamine, and we're going to react it with this alkyl tosylate. Enamines, remember, are nucleophilic at the alpha carbon. In the last question for the summary, we want to do a synthesis of converting this ester into a 1,3-keto ester. Enamines are nucleophilic at the alpha carbon, and they're essentially an equivalent, or they're equivalent to enolates. And so just like enolates, if we add an alkylating agent like this alkyl tosylate, this carbon will attack the carbon with the leaving group. So this carbon will attack here, displace this tosylate group, we're going to form this bond here in the product. And now the enamine under aqueous acid should be converted into a ketone. In the synthesis example, we're going to start off with an ester and we want to make it into a beta ketoester. That sort of screens the Claisen reaction. So remember, if we take an ester and we add base, we can do a Claisen reaction that typically gives you a beta ketoester. So keep that in mind. So in this example, we can use this ester that we're starting with, add base, and add an ester that is going to allow us to add the component shown here. All right, so our original ester is this one here. And from the alpha carbon, we're going to make this bond to an ester. Eliminate the leaving group, so the leaving group gets eliminated here when the alpha carbon attacks that carbonyl. So that gives us the ketone you see at the bottom of the slide, the keto ester that we see at the bottom of the slide. Then to add the double bond in between the two carbonyls, we can add base and formaldehyde. So this carbon would turn into an enolate, it would attack this carbon, and after dehydration, we would get a double bond there. And so that would lead us to the final product. Here's another example of a synthesis involving condensation reactions. So we're going to start with an ester, and we're going to end up with a beta ketoester that has this functional group here, the cyclohexyl group plus the nitrile. In this synthesis problem, we're going to start off with an ester, and we're going to turn it into a beta ketoester with a methyl group, and also we will add the cyclohexane that has a nitrile on it. To access the beta ketoester, we can do a Claisen reaction. So adding LDA to the ester will turn it into an enolate at the alpha carbon. That carbon can then attack the appropriate ester to do a Claisen reaction. So we can replace the methoxy group and end up with the beta ketoester that you see down here. So the right side up onto this carbon is our original ester. The left side is the ester that we added as a second substrate in the first reaction. If we add base to the beta ketoester, that should deprotonate the most acidic hydrogen, which is this one here. That would turn it into an enolate. And then we could add an alpha beta unsaturated nitriles through a Michael reaction. So the enolate will attack this carbon, get rid of the double bond, turn it into a enolate here, or enolate-like structure here, which then gets protonated by water or some acid in at the end of the reaction. That gives us access to this intermediate, which then we can turn into the final product by doing a methylation. So adding base would deprotonate the most acidic hydrogen, which is this one here, in between the two carbonyls, and then the methyl group will be added by adding methyl bromide.